The reality of heat recovery ventilation. It seems that we are in an ever-evolving world of building technology. We seemingly solve one problem, yet create another. When things are advancing this quickly, it is difficult to find the time required to properly evaluate these systems and their impact on a building and its occupants. Today we'd like to discuss the basic realities of heat and energy recovery ventilation. HRVs and ERVs are quickly becoming more popular in the building community as they have the ability to resolve a number of issues as well as enhancing indoor air quality. The T.H. Chan School at Harvard recently conducted a study relating to the cognition levels of people working indoors. They conclusively found that thermal comfort, continuous fresh air ventilation, and better lighting conditions resulted in cognitive improvement on the order of 26%. Changes in upcoming code cycle and Title 24 credits are beginning to reward the addition of HRVs. We wanted to take a quick look back at the recent past versus where we are presently. It is well known that older structures tend to leak more air. They are so leaky that they typically provide a limited supply of fresh air. This was acceptable when energy was cheap and seemingly plentiful, but population expansion and other factors have led to higher prices and energy conservation efforts. Energy efficiency measures were and continue to be a major focus of modern construction. This has done a great deal to resolve the energy conservation issue, but tighter, better insulated buildings have had a detrimental effect on indoor air quality. The air outside is typically 3 to 5 times better than the air indoors, and tighter buildings have allowed pollutants to concentrate to even higher levels. The easy and cheap solution was continuous exhaust-only ventilation. But in a tight house, where does this air come from? Attics? Crawl spaces? Interstitial spaces? It would be tough to characterize this as fresh air, and on top of that, it's not conditioned. So much for energy efficiency. Not to beat a dead horse, but it also resulted in negative pressure, which pulled uncontrolled moisture into interstitial spaces. I think we can agree that this was and continues to be a poorly thought out strategy. Heat and energy recovery ventilators are one way to intelligently address the indoor air quality issue, and they provide numerous other benefits that improve occupant health and comfort. These systems are typically balanced, bringing in fresh, continuous air from the outside while harvesting energy from stale air that is expelled. Incoming and outgoing air passes through a heat exchanger to recover the energy from the outgoing stream of air. The conserved energy results in energy savings and thermal comfort. These concepts are pretty easy to grasp, but people at various levels are having a hard time understanding performance issues and their impact on energy conservation and comfort. On the surface, it seems pretty straightforward. Watt draw, CFM, and energy efficiency specifications are entered into a software program and credits are given. One issue is that these numbers are not as transparent as one would think. A manufacturer might list maximum CFM for air delivery while listing energy efficiency at a different CFM delivery speed and watt draw at a minimal run speed. This is even confusing to those that deal with these things on a regular basis. In order to be transparent, metrics should, at minimum, be provided at standard operating speed. Speaking of energy ratings, one of the most critical is energy efficiency. In other words, what percentage of energy in the outgoing stream of air is conserved and imparted to the incoming stream? This chart shows the impact of efficiency on the temperature of incoming air. The difference between 60% and 90% efficiency is essentially apples and oranges. After reviewing these numbers, you may wonder why units rating even lower than 60% are being utilized to satisfy indoor air quality requirements. If a unit is at 60% efficiency, on a 40-degree day, fresh air is returned to the home at 58 degrees. How many BTUs will it take, and how long will the conditioning system need to run to adjust to 70 degrees? If a unit with 90% efficiency was installed in the same condition, it will return the incoming air at 67 degrees. Units that are substantially below 90% efficiency are negating a significant amount of the energy conservation gained from air sealing and insulation measures. Credits are given for air recirculation, which leads to gradual degradation of indoor air quality. This should not be a substitute for high efficiency, and crediting recirculation is questionable at best. Now that we've discussed the heat recovery units and their associated performance levels, we should delve into delivery systems. Delivery systems have as much to do with performance and outcomes as the units themselves. An engineered system of components is critical in achieving consistent and predictable results. Unless the system of engineered components is designed and supplied by the manufacturer of the HRV, an MEP should be hired to properly design these systems to optimize airflow in line with unit performance specifications. Tubing in non-conditioned areas should also be insulated. Many HVAC professionals seem to have a hard time disseminating requirements for high velocity, high volume systems like forced air units and low velocity, low volume systems like heat recovery ventilators. When they field engineered ducting systems for HRVs, the results can be extremely disappointing. Static in a low flow system must be minimized in order for performance to be realized. An engineered system of components helps them to understand duct sizing and other considerations that will lead to optimal performance. This is a good time to reassess our goals in regards to HRV and ERV systems. What should a consumer expect from these systems? If you look at the lists on the left and right, apples and oranges is a mild comparison. If the purpose of the HRV is to optimize energy recovery and provide fresh filtered air, that is what it should do. Low efficiency HRVs are creating a negative experience for those buying and installing inexpensive units and creating their own delivery systems. We may not be able to stop this from happening, but we should not be perpetuating it. Credits should be commensurate with efficiency and a proper delivery system. These are two things that will help ensure more predictable outcomes and attain the goals as stated. The following suggestions are submitted for your approval. We appreciate you taking the time to review this training, and we would be happy to assist with any follow-up questions regarding HRV and ERV units. For further information, please contact David Green. Thank you.